So today I wanted to tell you about a quite interesting fact in mathematics. So you might be familiar with this notation over here. Oopsie, this notation. It is n factorial. If you don't remember, n factorial is defined as the product of all the numbers from that number n down to 1 times 2 times 1. For example, if n was, let's say, 4 factorial, this will be 4 times 3 times 2 times 1, which is 24. Now, what is this symbol on the left hand side of the equality? Well, this is gamma, and this is the argument that gamma takes on. So, what is gamma? This is a gamma function, and the gamma function is defined as, let's say, I know this and f gamma of n is equal to the integral from 0 to infinity of e to minus n, t, times t to n minus 1 dt. And t is a variable of integration. You can also have x, or x here, or c, whatever, but the point is that it has this form. And if you were to take a number, let's say n is equal to, as your input, then your gamma function at 2 will be the integral from 0 to infinity of e to minus t times t to n minus, to 2 minus 1, which is 1, so t to 1 is just t, times dt, and then you will integrate this using integration by parts. It's something like this, and we have a very specific case, a pretty well-known case, which is gamma of 1, because if you have gamma of 1, here you will have 1 minus 1, which is 0, and then you will be left with the integral from 0 to infinity of e to minus t dt. And this is a very easy integral because it will simply be e to minus t, minus e to minus t, and then you evaluate from 0 to infinity, and this will be minus e to minus infinity, or rather the limit as a number e to minus a number n as an approaches infinity, minus e to minus 0, and this just goes to 0, and plus e to minus 0, anything to raise to power of 0 is just 1, so this becomes plus and 1. So gamma of 1 is simply 1. Now, how are these two terms related? How do we come up with this equality over here? Well, first, let's go back to the definition of gamma, and instead of taking just n as our input, we will take n plus 1. So we have gamma of n plus 1 is equal to the integral from 0 to infinity of e to minus t times t to n plus 1 minus 1 dt. And these ones will cancel out with each other. And we will be left with only e to minus t times t to the n. Now we can do this using iteration by parts. First, recall the ate. Remember that L stands for logarithmic, I stands for inverse, A stands for algebraic, and T stands for trigonometric, and lastly, E stands for exponential. And if you don't remember, this is a way to be able to tell which factor we are going to take as our U in our iteration by parts. So we have logarithmic in here? No, we don't. Do we have an inverse function? No, we don't. Algebraic? Yes, we do have an algebraic term. So we are going to choose t to the n is equal to u, and dv is going to be e minus t dt. So dv e to minus t dt. And to make this quicker, we are going to use the I method. So the I, if you want to know how to use this method, I will make another video in the future. But for a moment, I'm going to assume that you already know how to use this method, or that simply you can use the conventional integration by parts method. So plus minus plus minus, let's leave it like that. So this is t to the n, and we are going to get the derivative of this. And with respect to t, so the derivative is going to be n times t to the n minus 1. And again, we can go on and have n times n minus 1 t to the n minus 2. And here we are going to have n times n minus 1 times n minus 2 times t to n minus 3. And I think that you can see that it simply goes on and on. Now, what about the I part of this? If you have that your dv is equal to e to minus t dt, so here you plot e to minus t dt, and we integrate this with respect to t, which is only minus e to minus t. And then we can integrate this again, and the minus sign will disappear, and then it will reappear once again when we integrate it, and it goes on and on. So we can rewrite this integral like this. We're going to do this crossed t to the n times, I forgot this minus sign, so this minus e to minus t times t to the n. And now we can stop here and notice that we will have here a minus n times n to minus 1 minus e to minus t. And if you notice this, here we will have gamma again, but only gamma of 1. So this will be minus gamma, oopsie, minus gamma of n. I forgot, minus n times gamma of n, because these two account for the fact that it is gamma, but this is just a constant that we can take out of the integral. And there we are. And actually we will integrate this from 0 to infinity. And this is minus e to minus t times 2 to the n. And let's evaluate at infinity. So minus e to minus infinity times infinity to the n minus e to the minus 0 times 0 to the n. And this will simply go to 0. And actually, let's rewrite this as a limit. This is a limit as t approaches infinity of minus e to minus t times t to the n. And we can rewrite this as a fraction. So this is minus t to the n divided by e to the power of t. Well, actually, this is a limit as t approaches infinity, but I forgot to write it. And because of a certain theorem, we know that as a certain quantity approaches infinity, the one that is bigger will be the exponential. If you want me to, I can do a video on that theorem and explain why. But basically this will go to 0. And this therefore will go to 0. And look at this. We've got the next equality. And actually I forgot because I made a mistake here. This is not minus, this is a plus, because minus times minus is just positive. Negative times negative is positive sign. And we have gamma of n plus 1 is equal to 0 plus n times gamma of n. So let's rewrite it over here. N plus 1 is equal to n times gamma of n. And this is quite interesting because if you add only 1 to this, you to the argument of the gamma function, this will be the same as the argument times gamma of the same argument minus 1. So if you think of it, you will have the same. So if you have gamma of n, you can relate it with the same, but one less of the argument. So this will be gamma of n is the same as n minus 1 times gamma of n minus 1, but we can relate gamma of n minus 1 with one less of the argument. So gamma of n minus 1 is equal to n minus 2 times gamma of n minus 2, and we can keep going and write this as many terms as we want. We can even go to infinity if we wanted to, but I'm going to leave it like this. And now let's plug, for example, gamma of n here. So this is n times gamma of n, but gamma of n is equal to n minus 1 times gamma of n minus 1. So this equal to n minus 1 times gamma of n minus 1. But gamma of n minus 1 is equal to n minus 2 times gamma of n minus 2. So we are going to plug that in. So n minus 2. But I'm sure that you have assumed that gamma of n minus 2 is going to be equal to n minus 3 times gamma of n minus 3. So this will go n minus 3, and the pattern keeps on and on until we get to 1. Because when the value gets to, let's say, 2, it will simply go to 1. And we can restrict it to be positive. So in this case, this will meet the condition for gamma of n minus 1, of gamma of n plus 1 to be equal to n factorial. And this is very interesting because commonly we define the factorial for natural numbers, because it's basically the ways to arrange a number of things. And imagine, how would you arrange one half of things? There's no intuitive way to answer that. But in this case, we have a definition for it. Because if we were to say, I want to calculate 1/2 factorial, we wouldn't be able to calculate this and say, oh, 1/2, and then how would we keep going to multiplying this? This is impossible. But we will be able to do this by putting this into the gamma function, and 1/2 factorial will be gamma of 1/2 plus 1, which is gamma of 3/2. And recalling the gamma function definition, gamma of 3/2 will be the integral from 0 to infinity of e to minus t times t to 3/2 minus 1 is just 1/2 dt. And then you could calculate this integral. Now, I will leave this for you if you want to give it a shot. So, that's it. Bye bye, guys.